Okay, thanks for coming to what is this, week 5 of the intro course on a sunny. It's actually not sunny anymore. Damn. On a Friday though. Here's the attendance. Go ahead and do it. Also in the chat in the Discord again. So today we're doing Unit 12 as mentioned. Bruno lecture on it. Same thing as usual. One synthesis question on Tuesday. Project on Thursday. Take more time if you need it. It was midterms like this week, last week. I have one next week. It's weird. Yeah. This is in the chat. I'm going to change slides though. I lied. Oh, okay. Here was the responses. Spring 1. I guess, I was talking to the TAs earlier. I have allergies, so I wouldn't choose spring, but I think I would choose fall or winter. I thought summer would win, though. Summer always wins, I thought. But yeah. No? Yeah? You like spring more? Yeah. Okay. Well, I guess everyone's enjoying it right now, then. So that's nice. But yeah, I won't delay more, so...
Is the recording up? Yeah. Okay, cool. All right, everyone, so I'm back. We're skipping ahead to Unit 12 today, so not Unit 5, as mentioned. This is going to be pretty cool. This unit is kind of an interesting one. We were going to do like the visual system in the brain, but I talked to Chayden, and we thought this one would be more interesting, and we haven't run this unit before, so maybe everyone will like it. But I looked at the content for it, and I was thinking, like, what should I call this? And I thought a nice name for it is like the brain versus deep learning. So again, this is like neuro AI, not just AI that we're trying to like teach here. So I think today is like, since you've had like a little bit of intuition about like how these machine learning and deep learning systems work, especially with like the vision lecture last week, right? Yeah. So, and you've also had like a little bit of priming on neuroscience. You don't need too much, don't worry. But now we're gonna like kind of put them together and compare them. So that's like what we're going in with today. Yep, like I said. So I kind of like put it into like 2 parts. So the first thing is like the idea of attention in deep learning versus like neuroscience, like how do we pay attention to things? And if you might be familiar with like the transformer architecture, I'm not going to be going over that today. We have a language modeling unit for that, and Carter, who you may have seen, I'm pretty sure everyone has seen him. He made like a really good like blog post on that. So that's where we will be learning about like attention in transformers and language modeling. I'll actually be going over like attention and computer vision and how that compares to like sight in humans. And then also I have a small section on neuromorphic computing and also like the reason, like not the reason, but like a demonstration on how energy efficient brains are versus GPUs. So start off with an exercise. Everyone has like something to write on. Like every single table is a whiteboard, so if you need a marker, let me know. But
Typing is fine.
Yeah, I guess typing's fine too. I'll just wait like a second. Everyone just get like something out to like note something on because it's a small like interactive activity. So. All right. Everyone good? Oh wait, no. So what's going to happen is I'm going to advance the slide, and there will be some blue letters on the slide. You need to write down as many of them as possible, and they will only be up for like a short amount of time. Just try and get as many as you can. Okay? Everyone ready? So like, how many did you get? Like, just show of hands. How many were you able to like just like process? Like maybe not even like, yeah. See a couple, yeah, it was pretty fast, right? Okay. So that one was kind of hard. We're gonna do it one more time. Try and get as many as you can this time. So who saw the letter that time? Yeah, so everyone basically saw the one blue letter, right? But when there were multiple, it was very hard to like even, like capture like 2 or 3 of them. So, and I'm pretty sure, at least when I did this thing, my eyes basically snapped right to the K without like much thought. And you'd think, the same amount of letters were on both sides, right? But in the second one, you were able to filter out everything basically subconsciously. And in the first one, because you were like told to look for blue letters and there were a lot of blue letters, it was kind of a overload, so you couldn't process them all at once. Again, the same amount of letters are on the screen. So like, why are we able to much more easily like, see that K versus like all the other blue letters, right? Because if we talked about, like in computer vision, you are giving the model a snapshot of the world, like a static snapshot of the world, right? And if we were to ask, a network to like extract the blue letters and gave it those two things for the same amount of time, it would probably do well on both because it's not restricted by the same things that our brain is in the ways of attention. So this is from an MIT lecture that you'll be watching in the unit 12 on attention. And the takeaways from this, the lecturer said, was our brains have limited capacity to utilize what our retinas capture. So there is like some kind of like CPU speed going on here. Like we can only do so much with the information we're given, right? And this intuitively makes sense because there's a lot of information being beamed to your head at like one time. I'm seeing so many faces, so many colors. If I actually had to grapple and like fully digest all of that, it simply like would not work. I would not understand anything, right? And also like for selectivity, what's interesting is we kind of have this like inherent ability to just filter things out, like I said, subconsciously. They can kind of like just instantly find the K in there. So this is all just like a primer, like to get you thinking about like, why is it the case that one of those tasks was really easy for me and one wasn't? And why is it the case that, the way we've designed these computer vision networks, which originally is like, scanning across with convolutional filters, and that seems very intuitive, that obviously doesn't like carry over to like the problems we have here. So we'll start for like maybe, let's do 5 minutes or so. So given this information about like how you've seen how your brain can kind of grapple with this, how would you design an image recognition system so that this is inherent to it? Like, can you see a way to impose this restriction on an actual like computer vision system? And do you think it would have any benefits if it was, to be deployed? So turn and talk. I'll like call you guys back in like 5 minutes and just like think of whatever you can, and I'll ask some people to share. So yeah, go. All right, I heard some pretty cool things. So who wants to give it a shot? Like, what do they think? Like, how would they design a system that has like limitations or the power that we have? Oh, I get the cold call then, huh?
I would limit the runtime. So when it reaches a certain amount or like a certain period of time, it just dies.
Interesting. Yeah, that's one way. Yeah, we can only take in so much at one time. Anyone else? Anyone over there in the back right? You have anything to say?
Well, I was thinking like one way that you could focus more on specific applications is like how I had like edge picture kernels last week. So that's so we thought about research. So I found research from Chicago and they were doing like they're trying to get the model to imagine the space something with the image. So they can like identify the objects more accurately. And but it might be helpful, but not yet functional.
Interesting. That's cool. What's the name of the paper? Cool. Yeah, for sure. Awesome. That's cool. I'll do like one more. I think you had the same idea they had, so like just one of you say it, like whoever's comfortable.
Yeah, it's just about like filtering out all the images which don't have a B value, like you have the RGB. Everything that doesn't have a B value, you can just not count it, and then just look at images which have just B value, like whichever.
Mm-hmm. Yeah. So like for example, we put like cut the runtime and then that together, right? We'll have the ability to select for things very quickly, but if there's too many of them, we won't be able to get all of them, which is kind of what we saw, right? So that's one idea. And the benefits, maybe that there aren't necessarily any, but we're not looking for things that like perform at the same level as like a hyper trained like network, but things that maybe see the world more like a human does per se, which could have interesting applications on its own. So yeah, that was one of the exercises. All right, now I'm going to do a little more like lecturing on deep learning stuff. So I ripped these slides straight from the lectures I got last year on deep learning and vision. So I know they're good quality. They are very confusing though, so I'm only going to go over a high level of them. It was tough. I couldn't find anything in between this and like making it myself that would like make sense. So I know it's information overload, but I'll tell you what you need to pay attention to. So there's the idea of captioning an image. Just you give a model an image and it predicts like what's the first letter of the caption, what's the second letter of the caption, what's the third letter, so on and so forth until it's like, yeah, I think the caption should stop here, right? You'll go into more of like exactly how that works in the language modeling unit, like I said. But the general idea is like, you can see on the left there, you extract like spatial features with a pre-trained CNN, and you know what that is now because of last week. And then you have features, so a feature map, right, which is going to be usually, unless you have a lot of padding, smaller than the original image, and you want it to be smaller. What essentially happens then is you take this and you turn it from like an image into just a vector, right? And that first vector is like this initial, this H stands for hidden state, okay? So think of that almost as like kind of a memory of like what has been seen. And how this network architecture works is you save this into this context thing, which is like a little like just a representation of this essentially. And then you have a series of networks here, and each time you're like, okay, you give it a couple things. You give it the previous word predicted, you give it the previous hidden state, and you give it the context vector. So it sees a couple things there. It sees, all right, what word am I generating right after a certain word? So if it's like the, it knows not to generate like the again. It'll put the cat or something, right? That's the purpose of feeding in the previous word. The purpose of giving the context vector is so that we can actually give information about the image, right? And then once you give information about the image, you get a new hidden state, which is like a combination of the word, like the idea of the word, and the context vector. And then, then you give that again to the next state, next state, next state. I understand it might be a lot of information, but think of it as basically like you keep asking the network, okay, here's an image. What do you think the first word of the caption should be? Okay, great. You told me that. Here's the image again. And here's also the first word of your caption. Tell me what you think the next word should be, right? That's how this works. And that's what we're going to be asking the network to do. But like, the problem is like written right here. The input is like bottlenecked in C. Basically, the only point at which we inject information about the image to this network to let it actually generate the caption is during the creation of this context vector C at the very beginning. After we create that C, it's kind of static. It's like, here's what I know about the image. That's it. That's all you get. So now generate the caption based off of that, which isn't like the best, right? Like if you want a caption and the first half of it talks about the foreground and the second half talks about the background, you'd rather give it context about the foreground first and then the background later, right? So that it can actually attend, get where I'm going, attend to the right parts of the image, right? So you have like, the bottleneck is this context vector. So the intuition and what we're trying to go for here is like, how can we make, multiple like context vectors that give each like next token prediction information that is relevant to it, right? I use the example that you can keep in your head is like, first we want to talk about the foreground, and then later we want to talk about the background. But you can think for like like a bunch of stuff that's happening at once. You want to talk about the bird on the top left at first, then you want to talk about the ship, then you want to talk about the person in the foreground, right? And all those things are like, it depends where you look in the image, right? And if you pass in the whole image, like that information is kind of just combined and lost. So we're trying to like get the network to look at different parts of the image, basically, right? Does that make sense so far, the intuition behind it? I'm not going to be going over the math for this because we're not doing that. So just the intuition. That's all you guys need for this. Any questions on that? Like the kind of like the problem we have here with these image captures? No? All right, cool. So, right. And like I think I mentioned this in the beginning, but you'll learn more details about that. It's called RNN in like the language modeling unit. So here's like the first step to adding attention to vision, right? And while I explain this just on a high level, again, this is like math, you don't have to worry about it. On a high level, think about how this works with like humans, right? Like if I want to describe a scene, maybe first I'll look right in front of me and say, I see a window, and then I'll like, my eyes will move to the left and I'll describe Vibhav somehow. and then my eyes will look to the right, and I'll say something else about the color of the room. Like, I'm not like looking at like right in front of me and trying to say everything. I don't have the capacity to do that. So this is like how we put that restriction / like benefit of like looking at different places at different times into the network. You take the hidden state vector. Actually, first, before I go into this, any questions on what I just said? Like the motivation behind this? Okay, I'll keep talking, but please like immediately raise your hand if I say something that you don't understand. So we have the hidden vector just like from before. That hasn't changed. We create one of those. It's just basically a little feed-forward neural network. That's what this line is, right? Just turns it from an image to a vector, right? After some processing. And then what essentially you do is you take this vector, right? And this is the interesting part. You combine it in an intelligent way with the features that are extracted, right? So you're like, okay, here is the whole image, and how does the whole image and the top left of the image relate to one another, right? And you might say the whole image is like the ocean, and the top left, it represents the sky. And then so basically this little alignment score thing will be like to the network, if you want to see the sky, you want to look on like the top left or something like that, right? And you will basically create these alignment scores, which are like how, like what exists in these different parts of the images, right? And then what you do is you softmax them. And I believe we went over softmax, correct? Right? Turning just a set of numbers basically into a probability distribution that sums to 1. That's what softmax will do. And what the idea of this is essentially like, you can take this attention matrix and apply it to every step of this process. So you'll have an attention matrix, right? And you'll have one, I believe, yes, you will have one for each time step. So like the first time step, maybe for this captioning problem, you do want to look at the whole image to get the idea of it, right? And as you get to word 5 or 6, the attention weights over in the bottom right corner get closer to 0, and the top left to get closer to 1, right? And then 20 words in, only the center is 1 and the rest are 0. So it tells you, like, as you start making more and more of the caption, what should you look at, right? And you might be wondering, how is this learned? Backpropagation, like legitimately. If you can pass something through a differentiable system, it can like improve itself through backpropagation. So even though this sounds very high level and like arbitrary, kind of like how do you know when to start looking at different things in like the sequence? Through backpropagation, these attention weights will be learned, right? So the idea is we want to, at every step, we're making a prediction about something. In real life, it could be me trying to say something about the world, like captioning what I see in front of me. At every step of that process, we want to make it so that we're looking at different things. Because, like I said, if I look in one place and try and describe the whole image, I'm not going to be able to do that very well. But if I'm able to focus on certain parts of the image and use and describe it like sequentially, the performance is greatly improved. So that is essentially how attention works in vision, which I feel like people don't necessarily go over. I feel like most people's, like nowadays, their first introduction to attention is like in Transformers. It definitely was mine, but seeing it in the context of vision almost makes more sense because it's more intuitive to like attention to like detail or like looking at something, and then like as you start talking about other things, you drift off to like the more relevant parts of like the frame, right? So anyone have any like questions or comments on like attention and vision? It's a very high level description. Or like, yeah.
Let you know, like, what part are you going to focus on?
At like some time step t.
I mean, like from the picture to the vector, and then like first step, how do you know like what is the attention you're going to focus on?
So once the network is trained or during training?
Yeah, but there's like a bunch of things there. Then how do you decide like which one are you going to focus?
The network, like through backpropagation and learning, will figure out what part of the image, if it looks at this first, it does the best in the future, right? So maybe for like your data set, it's all like cat photos, right? So it finds it most useful to look at the cat first, which might be, based on this extractor, like it'll tell you where the cat is. Like, oh, the cat's over here, the cat's over here. Then it'll look there first, That's an example, right? That's how it knows where to look first. And maybe later it's like, then, whatever loss function I use cares less about the grass in the background, or if I do that, right? You could think of a situation where it's like you grade a captioning system on whether it gets the breed of cat correct, right? So then it would look for the cat first, and then everything else is like less important, so it would look for those like later, where the attention would be less focused on those areas, right?
Is there an attention matrix for every timestamp?
Yeah.
Like it then gets learned each time.
Yeah, so there's like, it's indexed by T, I, and J. I and J being just like the places, and then T being like the time step. Right? And then if I move to this slide, maybe this made it more confusing, maybe it'll help.
This looks like it evolves
Yeah.
over time. It doesn't it doesn't have a new one for each house.
I don't think it's explained super well, but like you can see it's like, it is indexed by time step T. And then over here, I think what they're trying to say is each of these attention matrices like makes the next context vector, right? As well as like it being given information from the previous hidden layer. So it's a little convoluted. Like I understand like there's a lot of arrows here, but how it's applied is like more like implementation detail. But like this is used to figure out what part of the image to look at. That's like the definition of the attention matrix.
So is the reason that you want to do this, like, because in a way, like, when you try to make peers more like human attention be inefficient, is the reason because you want to selectively focus on a few details like a human would, like, you want to focus on like a few things in an image versus like the whole thing? Like, what would be the reason behind like why some
Yeah, so the motivation for this specifically, there's like two answers. The motivation for this specifically was that, like I said, a model needs to encode everything it wants to say within C. Before we added attention, there was only one context vector, right? And that came from the whole image, right? Basically taking the whole image and saying, here's all the information you need to know. Now, network 2, make a caption, right? But now, over here, it's like, okay, here's the information you need to know at first. And now later on, model 2, like, take a look at this part of the image. So empirically, it does improve performance. That's like, I guess, the first thing.
it breaks it down into like not steps, but kind of
Yeah. And also, I think I'll get into this later, it also makes it a little more interpretable, because you can visualize its attention maps and see like, oh, it thought that like, for example, like it thought it was a dog in the photo, right? And you'll see like the attention map is like on a part of the tree in the background or something that like looks like a cat for some reason, right? It's like, oh, it got this wrong because it was looking over there. So then that's like, it's just more interesting. You can see like, why did this classify someone wrong, or why did it classify this wrong? It's because it was looking at the wrong thing, and you can see that now. So that's another reason. Yeah. Those are good questions. Anyone else? Yeah.
So how are we like identifying or like dividing out the photo? Is it like dividing it out based on the objects in the photo, the depth, the lighting? What is it using?
Are you talking about a specific matrix or just a general question?
Just in general.
A general question.
Yeah.
How is it dividing up? Again, this is one thing. It's like it tends to focus on objects, and we know this because there was another slide I didn't put in here. But you can use like these attention maps to then like do image segmentation. So it's like the caption is like the man. The attention map will be focused on the man, and we can crop that out, and now we have the cropped man apart from the image, right? So, but how does it end up learning to look at the man? Again, that's backpropagation. Mainly it's you tell it like what to update such that you improve the loss function, and it will converge on something that might make sense, which is like looking at a certain part of the image. So like, this was like, how does it, sorry, just to be clear, it's like, how does it determine what to look at? Or like...
No, what is it like actually looking at? I was asking if it's like looking at the person, looking at like the depth of the picture, the lighting, but you did answer it. It is looking at the person.
Yeah, I guess, yeah. More direct answer is like, we don't really know. Like, it's just the pixels and however it interprets those pixels, right? It doesn't have really like a notion of depth or anything like that, but it tends to focus on objects once it's trained. So that might tell you something. Yeah. Right. Anything else? Okay, cool. So I'm also going to go over this one thing. Where are we on time? I got time. So now I'm going to go over something really cool. And what's awesome about this is that like you all can do this like with the code that you have. It's really, 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 really not that hard. but the results are super cool. And it's like I think it's a fun first step into like explainable AI. And also, like, let me emphasize, it's like a first step. Like, this isn't like the most modern method in the world, but this is another way of thinking like, okay, attention is one way to figure out what a network is looking at, right? Like, okay, what pixels do you tend to focus on when you create this output? But that's kind of in a fancier network, right? Like, we're not going to ask you guys to make this. I mean, not yet at least, but so we're not. So like, how do we maybe ask like a standard convolutional network that doesn't have attention in it, what it's looking at, right? That might be a little harder because it's not explicitly in like the architecture, but it's very, very much possible, right? Like, so the problems up there, like given a pre-trained CNN, how can you figure out what it's looking at to give it a label, right? Because like, if you give it this yellow car, it'll say it's a yellow car. If you give it a red car, it'll say it's a red car. But like, what is it looking at to make that distinction? Which can be pretty important, right? Especially if you get something wrong. Like, why did you get it wrong? So like, the first solution over here to that question is like, visualize the filters, like the learned kernels. That is not very helpful, as you can see here. I don't know about you, but this doesn't make much sense to me. But you know, we can see kind of like, first it extracts like edges, and then it goes for like more like different shapes, and then it extracts more complicated things. But it doesn't really tell us what it's looking at. It just kind of tells us like everything it's looking for. So that's not a very good way to do it. I feel like I'm going to be met with silence by this, but anyone want to give a shot on a smarter idea? Give it a couple more seconds. Think about it. You can be wrong. Oh, yeah.
Give it an attention matrix and then see how that evolves.
That would be.
Or like, but then you're changing the network.
Mm-hmm. Yeah.
It's like you're trying not to change the actual network.
Yeah, we're trying to just use like the network and trying to figure out like, how would I know like, hey, like you can do whatever you want with the network, but you can't change it. How would you like get it to tell you what it's looking at?
Can I give it like different inputs?
Yes. Oh, that's close.
Like no, I'm asking. Like, can I?
Oh yes. Oh damn it! I gave it. Yes, you can give it whatever inputs you want.
Oh, I saw the slide. So
Yeah. Yeah, you get it right. Yeah.
You block off different parts of it. So.
Yep. So I'll go over here. This is the intuition for what Viv just said. Saliency, and just to be clear, saliency maps is basically like a map of what the network is looking at. So we want like a red region around the car, for example, right? So saliency via occlusion. I always say it occlusion, but I think it's occlusion. So here is a picture of a dog. I think most of us will agree that this looks like a dog, right? So a good trained network will as well. Probability of dog given the data X is 0.95, and probability of cat is very low. What if we covered up the top left, just like randomly, right? It doesn't change the probabilities much. You know, we crop out a little bit of its tail, but it's still definitely a dog. If we cover the face, though, now it's very ambiguous what that is. So by seeing the probability shift by covering up certain pixels, we know those pixels are important for the classification. Does that make sense? I thought this was super cool when I first learned it, because it's like, you could probably do this in like just NumPy, right? There's obviously smarter ways to do it, but just cover up random patches of the image, right? And then like see how the probabilities change for the class you care about. Any questions on that? It's like one way of doing saliency maps. Okay, cool. So yeah, I feel like this is relatively intuitive. So I hope you all understand it, because the next one is going to be a little less intuitive. But this is the idea. And so like, we want to, like, certain image patches, like those things we blocked off, are like more responsible for the output than others, right? So if you applied this like the elephant, you can kind of see like it's looking over here to figure out it's an elephant, right? Or like this is labeled as go-kart. This is what's most important for the label go-kart. If you covered this up, it probably would not say go-kart anymore, right? That's the idea. Like ship. And you can kind of see how it almost like is an outline of the important parts of the image. And this is kind of what I was getting at earlier. You can crop things out. Like, if I took this map and drew like a rough circle around that red part, I would be able to crop the go-kart out, right? So like with a plain CNN, you can do like image. You can extract a go-kart from an image, which is kind of cool, right? Through this method. So it's pretty powerful saliency maps. I think they're really cool. There is research showing that they might be misleading for bigger networks, but if you can see the stuff side by side like this, it really does seem intuitive. So, any questions on that? Anyone itching to go code this? Everyone, right? Yeah. Okay. So I'm going to move on to the next section. Any comments? No. Okay. Time. Okay. The next one is a little more of like an advanced way of creating saliency maps, and it's through backpropagation, especially with this is very doable in PyTorch. I'm actually working on a project where like my part of the project is like making saliency maps for like a language model, and it took like 20 lines. This stuff is super cool because of PyTorch. So a small tangent about how it works though. I don't think we went over like the actual like implementation details of PyTorch. We're just like kind of make this and start typing it. That's really all I need to know at the beginning, but something that's useful to know about like how PyTorch actually works. All these layers that you define in that model, they all have a forward method, like each of those little like dot relu or linear layer. They all have a forward pass, which is like what you see the image being processed through. And they all have also a hidden backwards method, right? That essentially will calculate the gradients for you. So this is kind of like what it looks like. You start off by doing this forward pass, doing all of these like different things, right? And then you like start, and then you like, all right, you save all this information, and then you calculate the gradients backward, right? So you build up this computational graph, like you need this, right? So this is, you don't have to worry too much about understanding it fully, but this is how PyTorch works. And if you take, I think it's still 493, it's a deep learning, then you'll like actually implement like something like totally from scratch. It's really cool. And this is why all it takes is loss.backward instead of having to like do math, which is like pretty nice. But like, why is this important? So the idea is, notice here, it's like we're taking gradients with respect to a variable. Like here's y1, here's the gradient with respect to y1. And what that basically tells you is like how much is, z going to change if I change x1 a little bit, or how much is z going to change if I change y1 a little bit, right? Now, these are just like tensors, like they're just, matrices and they're just like objects inside the computer. Well, another thing that is an object inside the computer that can be represented as a tensor is our actual image itself. So we don't have to just like, calculate on these like, it can seem kind of interesting, like, oh yeah, you put it into the model, black magic happens, then it spits out like a great like answer, right? But this is all still just math, and we can apply this math to our image itself. Like instead of computing a gradient to update the weights, we can compute a gradient to, and this sounds weird, update the image, right? We can calculate like changes to the image that will be useful to us. So here is like the formal definition of it. You have an image I, okay, and you can calculate the unnormalized class score. So for example, if it's like you give it a picture of this dog, and maybe there's two outputs, cat and dog, right? The logits, logits? Had we brought up that term before? Before you apply softmax to the output layer of a neural network, what is there before the softmax are logits, right? So it'll be like 5 and 7. That doesn't tell you anything, but the relative difference between 5 and 7 tells you that it thinks it's more of the second item than it is the first, right? But the logits are just the raw probabilities, raw items before they get turned into probabilities. But essentially just like, all you have to do is like not do softmax and you get the logits. Like that's it, right? So you will take the gradient with respect to the image. For all this time with backprop, we've been taking it with respect to the weights, like the actual like parameters of the network, but now we're actually taking it with respect to the input, which if you think about it is technically part of the network, right? It's like the initial stuff that gets passed into the network. And you can take this, and it's like, I'll show you, it's like, this seems complicated. It's like super, super, super easy. Yeah, and this is the English version. Take a second to read that. Oh, and right, before I mentioned, like the absolute value is there because gradients can be negative, but a negative value still tells us that it's doing something with that number, so we want to consider it as positive. Now, question, might be a little hard. Can someone tell me what the shape of this gradient will be? Any guesses? The shape of the gradient? Like if I was to like, say, plot it, or not plot it, but like just show it on a screen, what would it be? Would it be a vector? Would it be a matrix? Would it be like 3D? Would it be like some higher dimensional thing? Any guesses?
One per pixel.
Correct. It'll be the exact same dimensions as the input image, right? Because, for example, if you take a derivative with respect to a variable, a scalar, you get a scalar. Take derivative gradient with respect to a vector, you get a vector back, right? So take gradient with respect to a matrix, which is an image, you get a matrix back of the same dimensions. And again, what we're asking the network to do, I think this is a good way of thinking about it, is given this image and the class you think it is, right? So it's like, hey, here's a dog, you thought it was a dog. What pixels would you like increase to make it even more dog? Okay, that came out. So it's like what part of this picture, like if I was to make brighter or bigger or more, whatever that means, would you be even more confident that it's a dog, right? And we can get that in matrix form with the gradient. And all you do is just show that, and you get the saliency map. Basically saying, if you made these pixels brighter or bigger or whatever, I would think it's more of a dog. And that means that these pixels are important to determining that this is a dog. So that is saliency through backpropagation, which I think is super cool. Any questions? I get if how do I code this up? It seems pretty intangible, but I'll get into that in a second. But any questions on the method? Was that a hand? Anyone raise a hand? No? Someone want to fabricate a question for me at all? No? Nothing? Yeah.
What if the objects that you want have darker pixels instead of compared to the background?
That's what the absolute value does.
Oh.
So, yeah, no matter what, even if it's darker or brighter, it gives you a value.
Oh. Okay.
So, yeah.
So we're just disregarding direction.
Yeah. Okay. All right, I'll speed through this next part. This is the code. That's it. That's it. This is all what do you call it? Documentation. All you do is X is your input, you force it to require gradients, and then when you do backward, you just get the gradients of the image. That's it. That's the whole thing. I'll try and link a notebook later if anyone cares, but it really does not take that long. This is a significant amount of points for that one assignment, so it's maybe it's useful to know. Yeah. Dot view. It's dot reshape in a way that doesn't do some kind of copying or whatever. Yeah. Any questions on this? I promise I'll actually try and finish on time this time. I think last time I went 25 minutes over. I can't believe everyone didn't leave. Okay. Cool, right? All right. Let's go to this. So we have one more small activity. It won't take that long. But any questions on attention and vision, saliency maps via occlusion, saliency via backprop? Do you see any uses for it? I'll get one thing and then I'll move on.
Can you explain a little bit more about the code on the left side?
Yeah, for sure. So this is the method, and it might be a little small, but the method is just called compute saliency map. The inputs are the model itself, because you need that. X would be the image, and Y is the label for the image. Okay. The beginning, this top section of code, the smaller, it's not super important. The only line that's important is that we tell PyTorch, hey, X, the image, we care about the gradients. We usually don't, but now we do. So we care about the gradients. X dot requires grad. That's line 1 of the code, basically, right? Line 2 is actually running the model, like with the image. So it's like just output equals model X, right? You've already done that. The loss one, this is a little funky. This is some like PyTorch reshape wizardry that you have to do for like deep learning, but the short form of it and is essentially like, okay, get, and see we're doing Y there, right? Gather Y. The network gives you logits saying like 5, 7, 3, 4, whatever. And you know the index of the actual output, like dog is index 2, cat is index 3, gecko is index 4. And we have that in the Y, so we just get that like okay, here's the actual label of the image. We're basically just getting like what the network thinks the probability of that image is. That's it. This is the whole line essentially, right? Just getting that. And I can explain it later if you'd like. I can actually tell you what each part does. But then you just do backward, like I said, with the computational graph, which is just one line again. And then x.grad like equals torch.absolute value of x.grad is just me putting an absolute value on that. And like that's it. That's basically it. This Amax thing is to deal with the batch, but don't worry about that. Like this basically will tell you the answer. So yeah, that's the code.
Could you explain each extraction again? You gave the example of the network looking at like a bird in the upper left corner, but how does it actually determine where the objects are?
So I can answer that twice. For the attention and computer vision one, that's a little more complicated. What you would basically do is like visualize the attention maps over time, and maybe like in the caption there's the word bird that was generated at time step 5. Let's look at the attention map for time step 5 and overlay it over the image. It'll probably be more concentrated over the bird because that's when it said the word bird and it was looking at the bird. And what you can do is take that and just like draw a circle around that red part that's like says I'm looking at the bird, and then you extract it and it's like this is bird. Right. Does that make sense?
Yeah.
Right. Cool. Right. Oh shit. Okay, so I was gonna have one more like activity after this, but I'm just gonna leave you with this one like fun thing, okay? And once this is done, it's over. So we're gonna have this little activity. Notice as many changes as you can in the following images. It'll be like it'll flash for 1 second, and then it'll like go into a white slide for 1 second, and each time to like tell me like what's different about the image, right? Can you come up here for a second? I don't know how to do it. I don't want to like accidentally activate it.
Yeah. I don't know if I can see it actually. Oh yeah.
Oh. Okay. All right. Ready?
All right. I mean, like, write it down or just keep it in your head.
Yeah.
It
Probably
goes
your
by
head.
pretty fast.
Yeah.
Just try to remember as many changes as you see.
Stop. Okay. So what changed? Can anyone tell me what changed? Person? Right. Yeah, a lot of people say person.
There was this like bear thing or something.
Mm-hmm. Oh, yeah. 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 Good. Good observation. Anyone else?
So,
Yes. Great. All right. Yeah. See, there's a lot of things, right?
scooter.
Yeah.
Yeah.
All right. Sick. Now, I love this. Okay, I'm gonna show you the beginning and the end side by side. Did anyone see that? Like, this is actually what it was. Yeah.
I mean, for me,
Yeah.
when I first saw this, I didn't realize that like the color of the building
Yeah.
changed. Like,
This-
I thought that's it.
So many things are different, right? Like, look at this. Like, do you guys see that pop into frame? Did anyone that's one thing. Like this building is like it's pink now, right? Yeah. Yeah. So like yeah. So I mean, this is like really fun, right? So it's whack. No. Yeah, this isn't that like. Yeah, he's like, huh? Now you see it side by side, and it's like really, really stark, right? It's just pretty cool. Anyway, I don't mean to like do any more mind bending, but I'll just. All right, I think everyone liked that one. So I'll end off with one more thought, and then we'll close off for today. So this to me tells the importance of priors, right? Once you're told what to look for, like hey, the color changes, you'll probably be able to notice that a lot easier, right? And again, you can detect those changes side by side way easier than you can if you look at it sequentially. Computers don't have that problem because they have a very distinct memory. They can just save the damn image somewhere else, right? We can't do that. And then there's the idea of like limited capacity or processing power. So don't do the turn and talk. I know we're at time for now. Again, I talked so much we didn't get to like 2 of the sections, but I can add them to the unit or something like that. But yeah, anyway.
This will all be in the mega slide deck. And you guys ask great questions, so please ask in the Discord more. I don't know why it's so silent.
Yeah.
You guys don't need to be afraid. But it is dead.
Awesome. Hope you guys enjoyed it.
Send memes in it. Like, I like memes. Maybe I'll start sending some memes.
Send some stupid stuff, man. Like, yeah.
But yeah, thanks for coming.
All right, awesome.